In this video, I want to talk about the product rule for square roots, which the product rule for square roots is basically how does multiplying work with square roots. So let's look at the general rule, and that's any number times any real number a times any real number b within the square root can be broken up as square root of a times the square root of b. Okay, so this is the product rule for square roots. Again, let's go ahead and do an easy example to make sure that we understand that this is true. So I've pulled one here, and that's the square root of 12. So let's see if we can break this up and see if we agree. So the square root of 12, well, 12 can be broken up as 4 times 3. So far, so good. Now, by the product rule of square roots, I can break this up as the square root of 4 times the square root of 3. Okay. Now, the square root of 4 is actually 2. 2 times 2 is 4. So this would be 2 times the square root of 3. And square root of 3 is an irrational number. So this would be the simplified version of that. Okay. Now, you can go ahead and check on your calculator, are these equivalent? And these are going to be equivalent, okay? So you can check on your calculator and see, are these equivalent? And yes, they are. All right, so that's how you can break it up. All right, so let's go to a slightly harder example, and that's the square root of 300. So I need to think, is there a perfect square inside of 300? And what would the largest one be? So I found that 100 is in 300, so 100 times 3 is the same, and I can break this up by the product rule. The square root of 100 times the square root of 3, and so the square root of 100 is 10 because 10 times 10 is 100, and again, coincidentally, I'm left with the square root of 3. This is irrational, so I can't further simplify that. Okay, so that would be a simplified version of that. Let's look at an even harder problem and see if we can make sense of it. So I have 162 times a to the 5th times b to the 4th. So for this, I need to, once again, find a perfect square inside of 162. This isn't one that I have readily available, in my mind anyway, so I had to kind of pull it up. So I played with, is 162 divisible by 3? Yes, it is. Okay, is it divisible by 2? Yes, it is. So it's divisible by 6. Okay, but that 6 isn't a perfect square, so that doesn't help. Okay, is it divisible by 5? No. Is it divisible by 9? Yes. Okay, so it's divisible by 9. Awesome. When I did that, I found that I was able to find another square root. So 162 is actually 81 times 2. Okay, the 9's actually in there. And then this a to the 5th, I can break up as a squared. Whoops. Let's write this another way. A, then b squared. Okay, I'm really going to draw out the steps here so we can see what's going on. So a to the 5th could be written as a squared a, right? That would, the exponents would add to 5. And then b to the 4th could be written as b squared. Okay, now I can pull out all of the perfect squares. 81 is a perfect square, and that's 9. A squared is a perfect square. I can pull that out. A squared is a perfect square. I have to leave this 2 behind. I have to leave this a behind. B squared, I can pull out b. B squared, I can pull out as b. So what did I leave behind? 2 and a. And I can actually simplify this because this is a times a. So that's a squared. And this is b times b, which is b squared times 2a. Okay. So hopefully that helps, that you can break this up and you can actually just start pulling things out instead of breaking it up by the product rule. But product rule is what actually makes it valid, what makes this actually valid. Okay, so for the next thing I want to talk about is I want you to be be aware of adding square roots. So let's look at an example. The square root of 25 plus 144 is not equal to the square root of 25 plus the square root of 144. Okay? So, yes, please be cautious of this. For instance, if I add this on the left-hand side, that'd be 169. So 169 does not equal 5 plus 12 because this is 13 does not equal 17. Okay, so this is proof that you cannot add, if they're broken up by addition, you can't simply add them this way. I promise you there's going to be lots of questions in this homework and for the rest of our semester here and in future mathematics classes where you wish the rule acted this way. You wish that you could break it up this way, but you simply can't. It just isn't logically sound. So please be aware of that. All right. Now, I want to call your attention to some problems where we can actually add square roots if we're careful. So here I have 5 times the square root of 12 plus 2 times the square root of 3. Okay, so 5, and then I can break 12 up. Is there a perfect square inside 12? Yeah, it's 4. And then is there a square root inside 3? No, I just have to leave that. Okay, now the 4 can come out. It becomes 2. So I have 5 times 2 root 3 plus 2 root 3. I can simplify this 5 times 2. That's 10 root 3 plus 2 root 3. And now I can say I have 10 of these, 2 of these, so I have 12 of these. Okay? So that would be the final answer. So you can add square roots if they have these like terms in this way. Otherwise, I can't do anything. All right? Let's go on to another example. I have the square root of 5 plus 6 times the square root of 20. Is there a square root in 20? I think so. It's 4. Okay, so I can take the 4 out because it's a perfect square. Root 5 plus 6 times 2 times root 5. Now I can simplify that. That's 12 root 5. And now I have 1 root 5s plus 12 root 5s. I have 13 root 5s. Okay, so that would be my final answer. All right, that's enough for this video, but I hope that helps. And check out the next video for more square root problems.